Oh. So normally you can share your screen. I change the on Teams.
Oh, okay. But do you mind if I use Zoom? Because I've never used Teams before and I couldn't get it to work. So now I've asked people to join the class with Zoom.
Okay.
So,
oh yeah, okay, yeah, I see. Okay.
Are you the person that sent me the email? Yes. Oh, okay.
But I will send a message to the others to tell them that the meeting is on Zoom.
Oh, okay, thanks.
Sure they've seen.
Yeah, I mean, I sent them a message last night. I was working frantically trying to get this to share the screen, but it didn't work. So I sent a message at 9:30 last night. Well, okay. I think unfortunately no one's joined this yet. How do I make it more full screen? Okay. So I think I'm gonna start here. So let me introduce myself. Oops, that's no good. Hang on. Full screen old method. Yeah, that's better. Okay. So so I'm Rob Scott. I'm an on-signal chercheur or lecturer, researcher at UBEO, which is a university here in Brest, but I teach here at ENSTA just for this this class and the oceanography class because I'm an oceanographer and they want me to teach these classes on fluid mechanics and oceanography. So the plan for today is that I'll introduce the class and how it works, and then we'll get started on the topic of fluid mechanics, starting with a basic description of the macroscopic properties of a fluid. And sorry, I'm a bit distracted because I'm worried about the people. So some of the class is not physically here. They're held up in their own country, maybe, or in how do you say that, quarantine, I guess. And so I have to keep checking my email to see if somebody's like trying to reach me by email. I guess I'll hear it from that, or will you have you heard back?
On the meeting, I think, on the Zoom link.
They oh, I see. Okay, yeah. So Arnaud has joined. Okay, that's good. When it says two, that includes me, so that means we only have this Arnaud. Was there anyone else? Do you know?
Yeah,
who?
two more.
Two more.
So if you allow me, there are two persons from Tunisia. There is one person from Morocco and he's here for quarantine. And there is a French colleague who is also joining us from here, from France. So there are four persons. I don't know if they have all reached the link to join the meeting.
Okay. Well, on the positive side, these things are so there's one more. Okay, so we got 2 of 4. So hello and welcome if you're joining from elsewhere.
Hello.
Hello. And so I guess you can speak up like that if you have a question, which is probably a good idea. There's also a chat window in which you can type questions. But yeah, call out if you're finding that I'm not responding to your questions in the chat. And I think I'm going to leave it like that rather than full screen, and then I can see that chat window. Oh, okay. So we have 3 of 4 now joined us. I've also exceptionally left my phone on because I told people if they are in France, they can call me if they're having trouble. Maybe I'll start with a mention the resources for the class. So my favorite textbook on fluid mechanics is this. It's an old classic textbook by Batchelor. And unfortunately, the people who are not here can't see this, but I'm just holding up the book from Batchelor. I actually have the original 1967 version of the book, but there is a more recent version. And mostly we just need chapter 1. There's also course notes from that I'll call Arzel's notes because they're written by a colleague of mine from UBO called Olivier Arzel, who wrote them. And actually knowing that book and reading those notes, I could see that he took he learned the material or based his notes to some extent on Batchelor's work. Arzel wrote his notes in French, so if that's interesting to you, that's might make it easier for the francophones. So I present 4 classes of 3 hours each. We have a 15-minute pause in the middle, so we'll run till 11:45 today with a 15-minute break approximately at 10 o'clock. And I'll see you next or this week Thursday morning, so in a couple days, and then next week Monday and Wednesday in the afternoon. Feel free to interrupt me at any time. Just raise your hand, or if I don't see you, just call out. And as I say, if you're in the Zoom meeting, you can type in the chat. If I don't know, I'll try and follow it. But if you don't see it, just type here. Just type your question here. You can also send me an email. I think you have my email address because I've sent you all an email last night. But here it is if you need it. And I've emailed you a version of these lecture notes that I use. And I have them for all 4 lectures, but when I revise my notes for myself, I always change it a little bit every year, and it's usually very minor changes. But that's why I haven't given you all the notes yet. Yeah, in fact, I've already changed these notes. I changed the exercise, the second exercise, a tiny bit. So I'll re-email you the updated version, but the only thing that changed is that one exercise. There are many good books on fluid mechanics, but my favorite is this one from Batchelor. And I also recommend, I've been in science now for actually, I don't even want to count the number of years, but I can tell you that I studied engineering. Engineering physics was my first degree, which is supposed to be a slightly more mathematical version of engineering taught in Canada, and then I did a master's in chemical engineering and a PhD in atmospheric and oceanic sciences. And I can tell you that all throughout my career, I just felt like I didn't have the necessary mathematical background to learn the science that I wanted to do. And so I'm currently working on a textbook, Mathematics for Physicists. And I guess what my advice to you is to don't even if you don't like mathematics, try and learn as much as you can, because it's extremely useful for science. So I'm recommend. The problem is if you look at math books. So a good place to look, of course, is to look in the textbooks, right? But the problem is there's sort of 2 kinds of textbooks. There's textbooks written for mathematicians, and then there are textbooks written for scientists who want to use the math, and they're extremely different. And in fact, well. Here are some of the best books written for scientists that want to use mathematics. So Mary Boaz has written a very nice book. It's at some of you might know this book. If not, it's a very sort of gentle, easy introduction to math for scientists. Here's a slightly more formal, more recent book, but also well done at the sort of upper undergraduate level. So it should be easily accessible for you in a master's level class. Of course, I'm not saying that you need these books for this class. I'm just giving you my advice as a scientist who feels constantly frustrated that I don't know enough math, and I wish I had read a book like this when I was younger. Okay, so here for future reference, this is the material we're going to cover in this class. It's a short introduction to homogeneous incompressible fluid mechanics. And I guess that already sounds quite restricted, but we'll see it has very wide application for the fluid flows in the atmosphere and in the ocean. Which I think for engineering applications covers a really wide range of the problems that you'll encounter. So we'll learn about the properties of fluids. They're based on something called the continuum hypothesis. We'll spend quite a bit of time understanding the forces within a fluid, and then the key balances, in particular, starting with the most fundamental, the hydrostatic balance, just a balance between the force of gravity and the pressure gradient force, and Archimedes' principle. We'll cover the description of fluid motion, so the kinematics of fluids. The description of fluids falls into two general categories, Eulerian and Lagrangian. I have to tell you about the Lagrangian just so you know it exists, but we're going to use almost exclusively the Eulerian description. And there are some subtleties in describing the derivatives, in particular space and time derivatives of fluid quantities differ between these two different fluid descriptions. We'll learn the key conservation laws, starting with the conservation of mass, the incompressibility hypothesis, so the approximation that fluids are largely incompressible. You can't change their density significantly, and we'll see when that applies. We'll derive Euler's equation for and the generalization of which is the Navier-Stokes equation, which is probably the most important equation in fluid mechanics. It describes the time evolution of fluid flows with viscosity. So Euler's equation is the special case of Navier-Stokes equations when the viscous term is negligible. So don't I present this course at a more mathematical level than what I expect you to follow in detail. And I do that not to scare you. It's just that if you find that useful, then I want to provide that information for you. But I won't. Well, it's. the most important thing is to get the basic principles. We'll cover Bernoulli's principle, the momentum theorem, which allows us to calculate forces on objects that are embedded in a fluid flow, for example, a propeller or a turbine. And Betz's law will be a special limiting case of that. Okay, I should get some formalities out of the way, the notation and convention. So we're dealing with a branch of classical mechanics. So we need reference frames, and in this class we'll use exclusively inertial reference frames. So Newton's second law applies, and things will simplify if we use Cartesian coordinates, which I think you're used to seeing as written X, Y, and Z. But I prefer X1, X2, X3. And the reason is that this allows me to pass more easily to tensor notation, in which I would write the components of a vector just as xi, where the I is an index that can take a value from 1 to 3. Or if you like, you can think of the index as taking the values x, y, and z. So here's my Cartesian coordinate system with the x, y, and z coordinates, or I can alternatively label them x1, x2, and x3. And these are the little unit basis vectors, either I vector or E1 vector, E2 vector, E3 vector. So these are so I'm showing the two alternative notations for the same thing. So I think you've all seen the X, Y, Z and the I vector, J vector, K vector, but I like this other notation with the indices because it allows us to pass more easily to tensor notation, which just makes a lot of the manipulations much easier, especially in fluid mechanics. In more advanced areas of physics, it becomes indispensable. Okay, this is just, I think, familiar concepts, but expressed in the notation I'd like to use. So I have these two basis vectors, and I take the dot product or scalar product between them, and I'm, see, I here can take the values 1, 2, or 3. It's in the set. These indices are in the set of elements 1, 2, and 3. So I actually have 9 possibilities here, right? I have 3 possibilities for I and 3 possibilities for J. And what are the values? Well, they're 0 when I is different than J, and it's equal to 1 when I equals J. So this equation just expresses the what you can see visually here, that these unit vectors are orthogonal. So all the vectors that I'm going to use are Cartesian vectors, which means we make no distinction between contravariant and covariant components. And I think most of you probably haven't heard of contravariant, covariant, so just don't worry about it. But if you're someone who studied tensors, then we're using Cartesian tensors, so we don't distinguish between those. And even if you haven't heard of these things, contravariant and covariant, I think it's nice to at least tell you that there are sort of generalizations of vectors that even you think you've used vectors since certainly since lycée or maybe college, and they're so you know all about them, but they're as you get more advanced in math and science, they start generalizing things, and so the vectors you've seen are actually special cases of vectors called Cartesian vectors. So we use vectors because it allows us to simplify our description of physical quantities that have a magnitude and a direction. Not all things with a magnitude and a direction can be represented as a vector, but there are some things that can, for instance, the velocity. It could be the velocity of a particle. If we wrote the x, y, and z coordinates of some particle as functions of time, so this is a parameterized curve, if you like, but I simply mean I have three functions. The x is a function of time, y is a function of time, and z is a function of time. And if I take the time derivative of these three functions, that gives me the three components of the velocity vector of this particle. So I think that's a familiar notion, and I'm just showing you the different ways we can write that. So the final version is tensor notation, where I've written out the components of the tensor explicitly. So fluid mechanics is a branch of classical mechanics. So it's the study of the movement of material bodies. It's based on Newton's laws of motion. All three of them, remember Newton had three laws. All three of them are important, but the one we use the most is Newton's second law, which I think in French you call something different, but in English we just say his second law. But it's this one where the force equals the mass times the acceleration of some particle. But this is written for particles, and a large part of our job here in fluid mechanics is to transform these laws for particles to the case of a fluid that we're going to approximate as a continuous medium. Okay, so classical mechanics is based on this fundamental law of Newton, especially the second law, and then the forces follow from laws of interaction, and we also have the principle of conservation of mass in Newtonian mechanics. And I'll just mention that Newton's first law, okay, so I think we have all four remote participants joined us. Don't panic if you just joined us. The meeting will be recorded, and then I'll make that recording available to you. And it's going to be a massive file, so I have to work out the details on how I do that. But if you just joined us, you can ask questions by typing here in the chat. This is the chat. Or you can, you might have to reactivate your microphone and then sort of call out to me to get my attention. but feel free to do so. So we'll continue for another hour or so and then take a break. And then continue a 15-minute break and then continue till 11:45. So Newton's first law is this statement that a body that doesn't have any external forces on it will continue its motion, will either remain at rest when observed by an inertial observer, or continue its motion in a straight line at uniform speed. But from a modern perspective, this Newton's first law is really a statement that there are special reference frames that we want to give a special name called inertial reference frames, in which Newton's second law applies and takes this simple form. Newton's third law is will be used from time to time. In fact, later today, it says that for every action, there's an equal and opposite reaction. So what I mean is, if I press down, for instance, on the table, I'm applying a force on the surface of the table. The table is pushing back up on my hands with a force of equal magnitude, but in the opposite direction. So classical mechanics can be divided into two applications: particle mechanics and continuum mechanics. So fluid mechanics is a branch of continuum mechanics, where the continuum in question is a fluid. So what do we mean by a fluid? Well, fluid is a liquid or gas, and it's probably a little bit surprising at first, but it actually doesn't make much difference whether it's a liquid or a gas. Of course, it makes a huge difference if you want to pour something, right? You can pour your coffee because it's a liquid, and it's very difficult to pour a glass of air or something. But but when we're just talking about the dynamics of the fluid motion, it makes very little difference whether it's a liquid or a gas. They follow the same equations. Most liquids and gases are governed by exactly the same equation. They're Newtonian fluids, so they are governed by the Navier-Stokes equation, which is, so one of our main goals is to understand this Navier-Stokes equation, which is an expression of Newton's second law applied to these continuous media fluids. So we group gas dynamics and liquid dynamics into fluid mechanics because they behave essentially the same, and for that's the fundamental reason why oceanography and atmospheric science are actually very closely related fields. Most scientists like to distinguish, my field is really different from this other field. It's a little bit like countries, you know, like Canadians like to say they're very different than Americans, but even if they're not. And but in this case, it's as an oceanographer, I want to say we're actually very close to atmospheric scientists. So where the department in which I studied was the Department of Atmospheric and Oceanic Sciences, and I took classes with atmospheric scientists. Of course, there are differences, like there are clouds in the atmosphere, and we have salinity in the ocean. But in terms of the governing equations of the evolution of the fluid, they're very similar equations because they're derived from the Navier-Stokes equations. Okay, so thermodynamics is another branch of classical physics which will intervene from time to time in fluid mechanics, mostly through the equation of state, which is the equation which determines the density of the fluid. And it's also necessary for heat flow calculations, but that won't be our focus in this particular RAN3 class. Though I'm sure you'll do some heat flow calculations at some point. So I've already mentioned this. So we rarely solve the Navier-Stokes equations exactly in a given application. It's rare that can be done, but nonetheless, it's important to understand what we have to study the Navier-Stokes equations in any case in detail, because we have to know what it means. And the equations we do solve are simplifications of the Navier-Stokes equations, or we solve the Navier-Stokes equations with computer models, right, which simulate the weather, or there are off-the-shelf numerical packages that you can set up and solve the Navier-Stokes equations in an engineering environment, like the airflow in this room, for instance. So it's important to know what those numerical models are simulating. They're mostly simulating the Navier-Stokes equations will be a key element of that. And so we're going to derive the Navier-Stokes equations from the Newton's second law in this class. And we'll, I keep referring to the Navier-Stokes equations. These are the equations that apply to especially simple fluids called Newtonian fluids. And they're simple in the sense of having simple viscous properties. And we're also going to focus on the case of homogeneous and incompressible flows. By homogeneous here, I mean the fluid properties are the same throughout the medium, throughout the fluid. And I realize as I'm saying that raises the question, what do I mean? Like obviously the velocity can vary, and the pressure can vary, but so these are dynamical quantities. So we want to distinguish between dynamical quantities that we're solving for, and then parameters that describe the fluid, such as its density. When I say density, I mean mass density, right? The mass per unit volume. And I learned after several years of teaching here that in France, you don't necessarily mean mass density, right? You mean density in some more general sense, but in English, you can talk about other densities. But the default is mass density. So if I say density, I mean mass per unit volume. And so density is an important fluid property that we're going to assume is homogeneous. And the viscosity would be another parameter that we're going to assume is homogeneous. And incompressible means that you can't change the mass density or the density. Okay, so let's move on to a description of the physical properties of fluids, by which I mean liquids, both liquids and gases. most substances have stable property, stable states as a gas or liquid if the pressure and temperature are correct, and the density of the liquid is typically 1,000 times greater than the gas density at atmospheric pressure. As I say, the distinction between liquids and gases is really not important for fluid dynamics. They both are very similar for incompressible flows. I guess just to give an exception, the phenomenon of cavitation happens in liquids, but not in gases. So cavitation is when you're trying to run a pump too hard, and you create the pressure becomes so low that the liquid vaporizes in some region. It could just be for a short time interval. So that's the sort of phenomenon we're not going to deal with, but I just want you to be aware of there can be differences between a liquid and a gas in terms of fluid mechanics. So how do we distinguish a fluid from a solid? It's that solids have their own shape, whereas a fluid doesn't. That's kind of a obvious intuitive notion, right? If you pour a fluid into a container, or consider the gas in this room, it takes the shape of its container, and we're gonna. So this is a familiar notion. We're going to understand that at a fundamental level by looking at the internal stresses of the fluid, and we'll find that the internal stresses. I can't be more than vague about it now because I have to define what those terms mean, but the internal forces acting on the surfaces of the fluid depend on the fluid motion. So when the fluid is static, we don't have what we call tangential forces. So an important distinction that we'll make is between surface forces and volume forces. Yeah. And just, I guess, as I teach this, I always realize there are exceptions to what I'm saying, which is perhaps potentially a source of confusion. So you should be aware that, for instance, there's not always a sharp distinction between solids and fluids, or especially liquids, because you can, in some special circumstances, you can have materials that behave a bit like solids and a bit like liquids. So jellies or some paints would be examples of this. Even glass, the glass that makes the windows, it can in some sense be considered, normally we think of glass as a solid, but if you think on extremely long time scales, the glass flows downwards, right? So in the old churches here in France, I've never verified this myself, but I've heard that because these glass windows are extremely old, they're actually thicker at the bottom than they are at the top because it flows down. You can imagine other examples in geophysics, right? Where you have, I mean, the Earth is mostly made up of, or at least in the mantle and the crust, the outer part of the Earth, not the deep interior, but the outer part of the Earth is made up of rock, so that's a solid. But if you look on very large length scales and time scales of millions of years, this rock is flowing around like a liquid. So it's good to be aware of these distinctions, or these exceptions. But nonetheless, the distinction between a solid and a fluid like a liquid are extremely useful. Okay, so our main conceptual hurdle for today, at least, is to get around or digest the continuum hypothesis. So, as I said, Newton's laws were written for particle motion, but it's much more convenient to apply this to in fluid mechanics to a continuous medium, or that's what we mean by fluid mechanics. Is we're treating this fluid material as a continuum. Of course, it's not exactly true, right? Fluids are composed of molecules, the most basic stable unit. You'd have to do chemical reactions to break the molecules. So the molecules are like little particles. But we want to apply this second law of Newton to the fluid. So in principle, we could apply it directly to the molecules. And there are people doing that in biological applications, for instance. However, this is not practical in most situations, simply because there's 10 to the 23 molecules typically in or of the order of 10 to the 23 molecules in a given macroscopic fluid flow. And so the problem becomes much more manageable if we make the continuum hypothesis. So by that we mean we're going to ignore the particle nature of the fluid and approximate it as a continuous medium. So that's the main conceptual point. And I'm going to try, so that's the take-home message. And now I'm going to try and explain that and justify it in more rigorous detail. So let's imagine a cube with sides of length little l. So we could define the mean values of any key property we were interested in describing the fluid. That could be the density, the mass density, the pressure, the velocity, and how would we do that? Well, if we wanted to calculate the density, we would sum up the mass of each particle, each molecule that falls within our cube of length L. And so I is the index of the molecule number. So it would go from 1 to n, where n is the number of molecules that fall in this cube. And so that would give me the total mass here, right, of all the molecules. And I divide that by the volume, and that would give me the mass per unit volume. Now, if I define the volume as this, imaginary cubic surface within a fluid, imagine I did that in this room, there would be constantly particles entering and leaving the volume, right? So this density would actually fluctuate due to the molecular motion. So it wouldn't be exactly a constant in time. It would fluctuate. And if I moved it in this imaginary cube, I could move it around the room and it would similarly fluctuate as I did so. So I want to make this cube large enough that those fluctuations are small. On the other hand, if I made the cube really small, to really see this problem in an extreme of the fluctuations, if I made the length of the cube smaller and smaller, so it approached what we call the mean free path. So the particles of air in this room are bouncing around and colliding with each other, and the time in between collisions are called the free paths. And those free paths, they vary in length. Obviously, it's a random process, but they have a sort of mean length. So a mean free path. That's a quantity we talk about in statistical mechanics. And so the mean free path of the air in this room it's on the order of nanometers or tens of nanometers. I think a typical, it's about 60 nanometers or something, depending on the temperature and the pressure is around atmospheric pressure. But so if I made this cube on the order of tens of nanometers, then this density, which is the average, by definition is the average density within this cube, it would be this wildly fluctuating quantity, fluctuating wildly as particles enter and leave the cube. So in other words, we want we have to choose our length L much larger than the mean free path. So then the number of molecules in that case will be much larger than 1. But if we made, there's another trade-off. If we made L too large, if little l approached the length scale of the fluid flow. So the length, what do I mean by the length scale? I mean a length over which the properties we want to describe, such as the velocity, the temperature, the pressure, these things, if they're if those quantities we're interested in vary over length scales of the order of capital L, then there would be a problem if we made our cube so large that it was approaching that length scale, because then these averages would smear out the variations that we're interested in. So we'd be losing information about the flow. So the continuum hypothesis requires that there exists some length scale L intermediate between the mean free path, D, and the length scales of interest in the particular application. And then we have to, we don't actually have to calculate L or use L, we just have to know it exists. So we have to know that the mean free path is much, much smaller than the length scales of interest. Well, I've already mentioned that for air at room temperature and atmospheric pressure, the mean free path is on the order of 60 nanometers. So 6 times 10 to the minus 8 meters. So it's extremely small, whereas typically in engineering applications, we're interested in length scales. Depends on the application, of course, but centimeters, meters, perhaps millimeters in a very, small apparatus. But it's much, even millimeters is a million times larger than a nanometer, right? So we typically have this possibility of choosing a length scale that would be that would satisfy these inequalities in equation 4. And when you have that, then you can define, at least conceptually, you can define the mean density and the mean velocity could be defined as a mass weighted velocity of all the molecules, etc. So any physical property that we're interested in particular the density, the velocity, a component. So I've written U is the velocity, index I would be the ith component, or the pressure at some point in the fluid at some time t can be defined via these averages. When this condition applies, that the mean free path is much, much smaller than the length scales of interest. So then we assign those, at least conceptually, we assign these averages to be the property value at the center of the cube. So P is just the position at the center of the cube. And as we like to do, especially in engineering, we like to have dimensionless numbers that tell us when these certain conditions apply, right? So how would you come up with a dimensionless number here? Well, we want the mean free path to be much, much smaller than the length scale, right? So why not take the ratio of the mean free path to the length scale? And so that's what Knudsen did, and this is Knudsen's number, and we want the Knudsen number to be much, much less than 1. So an often cited tolerance is that the Knudsen number should be less than about 0.01. So you want your length scale to be 100 times larger than the mean free path, which is almost always the case in engineering applications. When it's not case, for a gas at least, we call it a rarefied gas. So I'm just giving you some terminology here. So you almost never need to consider a rarefied gas, but it's important that you're aware of where these approximations come from, the continuum approximation, so you know the range of validity of the information that we're going to be using. So you can imagine in cases where this wouldn't apply. Well, maybe just to give you a little anecdote of, I worked as an engineer after I did my first degree in engineering, and Canada was getting involved in the International Space Station, and they built this arm that got the Canadian arm that goes on the space station, and they some engineer wanted to do some measurement of the thermal conductivity of some part that goes on this thing, but it had to be tested in the conditions in which it would be used, right? Which is essentially in space, so extremely low pressure. So we had to. So I was assigned to do this. So I had to put it in a vacuum chamber and pump out all the air before we did the measurements. And so it's rare that these situations arise, but you should be aware that they can arise. Also, I guess well, anything in the upper atmosphere becomes a problem with a rarefied gas. Yeah, there's also situations in biology where you want to consider the individual molecules and the reactions between them. So that might be, well, but the applications you're mostly concerned about here are with flow in the atmosphere near the surface and the ocean. So the continuum approximation applies to a very, very good approximation. Okay, so we have in fluid mechanics, we a big part of our job is to understand the internal forces in a fluid, and conceptually we divide those into two types of forces: volume forces, also called body forces, and surface forces. So these body forces are much easier to deal with than the surface forces. So let's start there. The body it's a little bit hard to explain it conceptually, but it's very easy to treat it. Maybe it's best to just give you the example that is the most important one for us, and then you'll have a context for it. It's the we're really talking about the most important example is the force of gravity. So I want to call that a body force or a volume force, because the force of gravity applies if I take any object. It doesn't even have to be a fluid, it can be a solid, but also true for a fluid. The force of gravity applies throughout the solid, right? Every little bit of the book is being pulled by gravity. That's not the case for surface forces that we're going to treat later. Like if I apply a pressure on the top of it or something, that's treated differently. So So that's why we make this distinction between body forces and surface forces. If you try and put that into words, it becomes a little bit more vague. The body forces are capable of penetrating into the interior of the fluid and extend over very long distances and very slowly. So why didn't I just say it's constant? Well, it's actually not perfectly constant, right? The force of gravity, for instance, is stronger closer to the center of the Earth than when you're farther away. But you know, for most applications, that difference is absolutely tiny. So it can be ignored. But technically, I have to say the force of a body force very slowly. It's almost identical throughout the fluid parcel, and is essentially uniform for small volumes. And so it makes sense to talk about the force per unit volume. That's another way to define the it's sort of a backwards definition, but at least conceptually you can ask is this a volume force or body force? Well, you can just ask yourself, is it convenient to describe it as a force per unit volume? And if it is, then that's a body force. Actually, I can't resist to give you an example where this really shocked me. I had I was talking to a friend yesterday who was working, he's an Icelandic friend, and he's working on sea level rise in around Iceland. And he was talking about storm surge causing the water to go up in near Iceland, and the threat, and that's changing with global warming, with the increasing sea level rise, and you know, maybe it's getting stormier, and so he's modeling this. And I said, but hold on, Greenland might melt its ice sheet, and that's just going to be much larger than any signal you're talking about, right, with your storm surge. And he said, no, if the ice sheet melts, the sea level will go down around Iceland. I said, what are you talking about? Sea level is going to go up if the Greenland ice sheet melts. He said, no, because of the gravitational attraction of the ice sheet is so important that's pulling water towards Greenland, and Iceland's not so far from Greenland, so it gets some of that, it feels some of that sea level rise due to the gravitational attraction of the ice sheet of Greenland. And so if it melts, it gets spread out all over the Earth, and so you lose that gravitational attraction. So even though global sea level has gone up, the sea level near Greenland and even as far away as Iceland will actually go down. And this just blew my mind. But then, well, maybe if any of you, I should pause there. But if any of you are interested, I can. He showed me the graph that you know, of the scientist who did the. It turns out I actually know her, the lady who did the analysis that proved this. Sorry.
So with this discovery from your friend, we should not worry about global warming or anything like that.
You should not worry about sea level rise if you're close to Greenland. But
what you are saying is that it's only local around Greenland, right?
Yeah.
Nothing global level.
And it's worse in the tropics. Yeah, because it's yeah. So yeah, thanks. It's not. You should be very worried about global warming and about sea level rise. And but there can be these local surprising effects where I guess I told this story because I just found it amazing that the gravitational attraction of an ice sheet could make a difference on scales of hundreds of kilometers. But yeah, globally, the sea level goes up, especially in the tropics, and it's a huge concern. Yeah. Yeah, and an enormous concern, even more relevant than the Greenland ice sheet, is the Antarctic ice sheet, which would cause many meters of sea level rise. Okay, so as I started by giving you the example of a body force that's going to be essential for us, which is the gravitational attraction of the Earth. So to a very good approximation, I guess this helps or show the notation as well. So the force is a vector, and I put a little g here to indicate due to gravity at the point P in the fluid at time t. So we can replace P by the XYZ coordinates or the XI coordinates to indicate the position, equals minus because it's the unit vector K is typically chosen to be the unit vector upwards. What's up by definition? It's in the direction of or opposite the direction of gravity, right? So by definition, gravity is in the opposite direction of this unit vector K, or by this convention. And it equals well, here's another convention. We write the force of gravity per unit volume. So little g, the 9.8 newtons per kilogram, is the force per kilogram. And so if we multiply that by the density, the mass per unit volume, then we get the force in newtons per meter cubed if we work in the SI units. That's one example where the Anglophones have followed the French and didn't invert the acronym, right? So in English we say SI for, I guess, System International, right? Okay, so as I say, by far the most important body force for us is the gravitational force of the Earth, which we treat in this way. Just to be aware, you'll also take with me the class in oceanography, and then we'll see inertial forces. Inertial forces arise when you use non-inertial reference frames. The most important is the Coriolis force. There's the centrifugal force and the Coriolis force. And the Coriolis force is a body force as well. Just for interest of full disclosure here, if you're ever, you're engineers, so you can imagine working on a plasma, I guess, and so that would be a case where, so a plasma is a fluid that's electrically charged. And so then the electromagnetic forces would be body forces. So there are other places, there are other body forces than gravity, but for us it's mostly that. Okay. Let's move on to surface forces, which unfortunately I think conceptually are also easy to understand, but when you get into the mathematical description, it becomes, I think that's the main challenge of this class, and it's one of the main reasons we had to introduce tensors, is because the surface forces are, well, mathematically they're Cartesian tensors, or they're most easily represented by Cartesian tensors. Okay, so let's, I won't get through all of this before we take a break, but let's see how far we can get. Well, so just conceptually, the surface forces are those that are most easily described as a force per unit area. So where did they come from? Well, they're of molecular origin. So it's interactions between molecules. So an example would be if I push on this book that applies a force on the surface of the book. I say it's of molecular origin because not because there are molecules in my arm that, you know, that did the action, but rather the interaction between the surface of my skin and the surface of the book. That if you can sort of imagine that on a, you know, viewed through a scanning electron microscope, you would see a bunch of molecules from the two media coming close to each other and then interacting, well, electrostatically. It would be the main interaction between them. But even without getting into what force it is, it's just, it's the force between those molecules, right? That's transmitting the force from the one body to the next. And even with that, or leaving it general in that sense, you can imagine that these forces decrease rapidly with distance, and they require direct contact, or contact at least in terms of molecules. So the molecules are close enough that the electrostatic forces between them, or even forces of quantum mechanical origin, become important. So let's consider a fluid, for example, the gas in this room, and then imagine an imaginary surface in separating the you know, through the fluid. We often call that a control surface in fluid mechanics, but it's just a technical word for, you know, an imaginary surface through the fluid. There will be some of the fluid will transport momentum across this surface, and as it's carried as the molecules cross the surface. Molecules are bouncing around randomly, chaotically, and with them, each one carries a tiny bit of momentum with it. So these molecules migrating across the surface randomly cause a transport of momentum. Okay, thanks. So in liquids, the surface forces can be more complex, but the details don't concern us here because we're doing continuum mechanics. If we were trying to do particle dynamics, we'd have to represent those forces explicitly, but we're going to treat our media as fluids, so continuous media, and approximate these forces as either body forces or surface forces. Okay, so because the forces are so short range, a fluid volume interacting with an adjacent volume will be exposed to these short range forces only within a boundary layer of order the mean free path. So when I say they're short range, I mean they're of the order of the mean free path of the fluid. And so we're going to, on our sort of macroscopic description of these fluids, these forces become forces per unit volume. Surface forces become forces per unit area, even if on the microscopic scale, of course, they extend over a three-dimensional volume, or they're due to interactions over some volume. The volume is very thin. So the total, on a more practical level, the total surface force on a fluid volume is obtained by integrating the surface force per unit area over the surface bounding the fluid volume. We'll see plenty of applications of that. So what are these surface forces I'm talking about? Well, there's pressure, and the viscous force is a force per unit area, or a surface force as well. And so both of these are represented by the same tool, the same mathematical entity called the stress tensor. Yeah, this is a mathematical device called a Cartesian second rank tensor. And I think I can just have time to go through what I mean by a tensor. It's not necessary to become mathematicians and work with tensors in all generality, but I think it's useful. In most courses in fluid mechanics, you have to use tensors, even if most of you, or many of you, have probably taken fluid mechanics before, but your teachers probably didn't talk about it in terms of tensors, right? But you're actually you're using tensors without giving them the name. So I like to just tell you what these mathematical things are, because they're extremely powerful and useful tools, even if we don't have time to go into great generality about tensors. So tensors are simply generalizations of vectors. They're indispensable in fluid mechanics, but you also use them in solid mechanics whenever you talk about stresses inside a beam, for instance. They're used very generally in physics and in geometry. I guess maybe maybe the most familiar for you would be the, well, maybe you've heard of stress tensors, but also the moment of inertia tensor, or the, yeah. So if you want to describe a spinning top and its resistance to acceleration when you apply a torque to it, then the generalization of mass that's applicable for when you apply torques as opposed to linear accelerations or linear forces is the moment of inertia, which is a rank 2 tensor. Okay, so we're only going to deal with Cartesian tensors that make no distinction between these things called covariant and contravariant components. Don't worry about it if you don't know what that means. Well, a rank 2 tensor has 2 indices. So the rank is the number of indices. So we've already seen rank 1 tensors. Those are just vectors, right? So at the very start, I wrote the velocity vector is u with a little arrow above it, because I think that's the most familiar notation. But I also wrote it with u subscript I, and I said, look, I is an index that goes 1, 2, 3 for the 3 different components. So that we're treating it as a tensor. It's just a rank 1 tensor, rank 1 because it had the 1 index. But you can imagine you could have 2 indices, right? And then that would be a rank 2 tensor. You can write well, here's my rank 1 tensor. We could write it as a column vector or as a row vector. It's usually more convenient to write it as a column vector. Rank 2 tensors in 3-dimensional space. Or actually, maybe before I get into that, I'll say, notice I have 3 components here. It's a rank 1 tensor, but it has 3 components because we're in 3-dimensional space. Okay, if I go to a rank 2 tensor, and I'm still in 3-dimensional space, I'm going to have 3 times 3 components. Well, I can write that as a matrix, right? I could write that as a 3 by 3 matrix. So rank 2 tensors look just like matrices, and you multiply them by matrices. So why call it a tensor and not just a matrix? Well, you could call this a row, or sorry, a column matrix if you like. You could call this a 3 by 1 matrix, but it's a special matrix, right? It's a matrix where we have some physical meaning attached to it. We mean that if I rotate, it's expressed in some coordinate system, and if I rotated the coordinate system, those components would change. They change in a very particular way, depending on the rotation. Well, without going into the details, there's some rule for calculating your new components from the old components if you change the coordinates, if you rotate the coordinate axes. The same is true for the tensors. If you the second rank tensors, which look like a matrix, a 3 by 3 matrix, if you, in one coordinate system, if you change your coordinate system, then you have to apply some rule to find the new components of that tensor. So a new matrix in the new coordinate system. So it's just a conceptual point that matrices are very general things. They're just are very simple things. They're just collections of numbers organized in a table. But if you want to attach physical meaning to it, then one physical meaning you can attach to it is a tensor, which means it's a vector in the same sense as we're attaching physical meaning to a vector, and yeah, so here's a particular example of like gravity is the force of gravity, as we've said, well, per unit mass is just minus g in the z direction, or minus z direction. So if I wrote that in one coordinate system, it'd be 0, 0 minus g. But if I happen to, it'd be non-standard, but I could choose to have the x-axis in the vertical, and then in that coordinate system, I would have the same force, same vector, written as minus g, 0, 0. So these are just different. So the components change depending on the choice of the referent of the coordinate system for the same vector. Same is true of tensors. If you change the coordinate system, you change the components of the tensor, you change the matrix, but it's the same tensor. You've probably seen some tensors. You've probably seen stress tensors, or if you haven't, don't worry about it. But I just want to touch base with some of the things you might have heard of. Stress tensors, the inertia tensor, or the moment of inertia tensor. Another tensor you've almost certainly seen is the Kronecker delta, this delta ij. Well, we saw it earlier today, right? I used it, but nobody stopped me. So I assume you've seen this. It's just defined as +1 when the I equals j, and it's 0 when I is not equal to j. So that's a rank 2 tensor. It's rank 2 because it has 2 indices. And now I and j can take on values, well, typically 1, 2, 3, if you're in 3-dimensional space. You can imagine being in a higher dimensional space, and then it would take on, I and j would take values 1, 2, 3, 4, for instance, or in a plane, they would just take the values 1, 2. But in all cases, it's a rank 2 tensor because we have 2 indices. So you can write it as a matrix. It's the identity matrix in 3 dimensions. That would be a diagonal matrix with 1, 1, 1 along the diagonal. Another tensor is a rank 3 tensor, has 3 indices, epsilon ijk, and it's called the alternating tensor, sometimes called the totally antisymmetric tensor, and it takes the values +1 or -1. That's the only options, or 0, sorry. It can also take the value 0, but it takes +1 when the I, j, k are even permutations of 1, 2, 3. And it takes the value -1 when I, j, and k are odd permutations of 1, 2, 3. And this epsilon ijk, or alternating tensor, is extremely useful. You can use it to represent the cross product or the vector product between 2 vectors. So in tensor notation, you would write the kth component of w, this vector w, which is the cross product of vectors u and v. Sorry, I guess you use different words in French, right? This is the vector product, and sometimes in French you write it with a wedge here, right? Rather than the cross, but in English we call it the cross product, or I guess vector product as well. And so the kth component of this vector W is the ith component of U times the jth component of V times epsilon ijk. And now there's actually, it's implicit here that there's a summation over the repeated indices. What are the repeated indices? Well, there are two i's here. So I is a repeated index. So we have to sum over I. And there are two j's here. So we have to sum over j. But there's only one k. So we don't sum over k. Now k can take the values 1, 2, and 3, of course, because we have 3 components of this W. So the way to read this is, okay, I can set k as a free index. I can set it equal to 1, 2, or 3. Let's set it equal to 1 on the left-hand side. So I set it equal to 1 on the, or sorry, on the left, I set it to 1 on the left-hand side. I set it to 1 on the right-hand side. And then I let I, well, then I sum over I and I sum over j. And I just apply these rules for epsilon. It's 0 when, if we start at 1, 1, 1 here, so I equals 1, j equals 1, k equals 1, then epsilon is 0, so we don't add anything. Then you can let I equal 2, j equals 1, k equals 1. Well, it's still 0. So we have to get to the point where I, j, and k are different. So there's only two options when k is 1 that are non-zero. It's I equals 2 and j equals 3, or I equals 3 and j equals 2. Okay. So then when I is 2 and j is 3, that's a 1, 2, 3, that's an even permutation. And when I is 3 and j is 2, that's an odd permutation. So now you have to know, yeah, so here I've written out the summation explicitly. And I've told you it's called the Einstein summation convention. Yeah, I guess the truth is, for years I was working with this and I never knew in all generality what an even and an odd permutation was, but I knew how to recognize them. So maybe that's all that's necessary here. Yeah, if you're interested, come to me in the break and I'll explain what an even and odd permutation is. But but we can recognize them here because we just have 1, 2, and 3. So the even ones are whenever you go to the next one, you're going either, or you're always going in the same direction. So even would be, well, 1, 2, 3, or if you can get to it just by sort of shifting them along, then it's an even permutation. So if I shift these all to the right, so the 1 goes here and the 2 goes here. What do you do with the 3? Well, it's cyclic, right? So you would put the 3 back at the start. So 3, 1, 2 is an even permutation. And we could shift it one farther. So then you would have the 2 would become here. So it would be 2, 3, 1. That's another even permutation. If we shift it further, well, we get back to where we started, 1, 2, 3. So that's an even permutation. And I guess you could shift them in the other way, but you won't learn anything new. You'll just get 2, 3, 1. If you shift them all to the left, the 1 drops off to the left and you have to put it back here. So we'd have 2, 3, 1, still an even permutation. So how do you get an odd permutation? Well, you have to interchange 2 of them. So if I interchange 1 and 2, so I'd have 2, 1, 3. I couldn't notice that's an odd permutation. I couldn't get there by doing the shifting thing, right? I had to interchange, and if I do one interchange and then do another interchange, I fall back on an even permutation. So two interchanges give you an even permutation, and one interchange gives you an odd permutation. In fact, it turns out, well, I can tell you in all generality now, an even permutation is constructed by an even number of interchanges between any two of the elements here. In this case, indices. But this is a general thing. We could have permutations of I guess the people at online can't see this, but if you take any three objects, you can, or any number of objects, but let's say three, you can do permutations of them by interchanging their position. So they have to be an ordered set of things, and then you can do permutations. To define even and odd, you have to have a starting position that we all agree that's the even position, or the starting position. In this case, it's the numbers being in order 1 through 3. Yeah, it's I find it kind of interesting mathematically that there's no contradiction here, right? There's no, like, you can get to the same arrangement by doing different rearrangements, right? You can, but there's never a contradiction between what's even and odd. It always takes an even number of interchanges to get to some even permutation, and it always takes an odd number of interchanges to get to an odd permutation. So that's what they are, but in all generality. But in our case, you can easily recognize the even permutations as the ones that you obtain by this sort of shifting of the 1, 2, 3. Remembering that it has to be cyclic, so if a number falls off to the right, you put it back at the left, etc. So this might look like a way of making the cross product more complicated, but remember, in order to evaluate this cross product, you probably had to do some different people have their different ways of doing it, right? But you probably have some geometric way of writing down the unit vectors I, J, and K, and then the next vector U, and doing some permutation of those. Has everyone seen this, or who has seen this vector product before? So only sort of half of you have seen the vector product. Okay, what about the scalar product or the dot product?
Yes.
Most of you have seen the scalar product, but not all of you have seen the vector product. Okay. Well,
I think most of us is the first time we see this notation of vector product.
the
X instead of the.
Oh, okay, but that's just notation. So, but most of you have seen the vector product, or right? So it's a way of getting a new vector from two old vectors, and it gives you. Maybe I should tell you some properties of it. We're kind of delaying the break here, but it gives you a vector that's perpendicular. So the vector W is perpendicular to U, and it's perpendicular to V. Yeah, maybe I should, well, unfortunately the people at home won't see this, but let me, oh, hang on. I could just, I think I can stop sharing and then go video, right? Can you, for the people at home, Arnaud, can you see me?
Yes, we can see you.
Ah, great. Okay. So then you can see my attempt at showing three vectors with three pens. So if I take two vectors, they form a plane, right? And as long as they're not parallel, two non-collinear vectors. Then if I take the cross, so that, say the black one is u and the blue one is v, then if I take the cross product between vector u and vector v, I get a new vector w that's perpendicular to, so I guess it's a little hard to see this, but it's perpendicular to the black one, the u, so this is my w, and it's perpendicular to the blue one, the v as well. So w is perpendicular to u and it's perpendicular to v. So that defines its direction. I guess it could be there or somewhere on that line. But actually, and which sense it has is defined by the right-hand rule. So I'm just realizing it actually should be, actually let me change them so that, just so it's easier to hold. So this is going to be u, so I put u over here and v there. So that with my right hand, if I put my right hand in the direction of u and then bend my fingers towards v, then my thumb points in the direction of w. So that's called the right-hand rule. Okay, so the only other option was that it was pointing down, but so we use the right hand to define which of the two possibilities it is. So that's the vector product. Are there any questions there about the vector product?
Yes, I have a question, please.
Okay.
U and V must have the same dimension?
Yes, they must have the same dimension. These have to be like three-dimensional vectors. And then they produce a new third three-dimensional vector.
Okay.
Yeah, otherwise we'd run into trouble with the indices here. And again, there's an implicit summation over the repeated indices, as I said, as I've written here. I think it's maybe, let me just give well, actually, let's stop there and then we'll take a 15-minute break. So we'll come back at 10:31. Yeah,
right.
We can go through this table then. Okay. Nice American voice. Okay, can I? Yeah, so you can say, so this isn't essential material for the class, but but just I was a little bit concerned that I'm very glad that that you asked that question, so that I have my chance to explain that global warming is a very serious thing, and I hope that, or I assume that's partly why many of you are here, right? Is to develop renewable energy resources, but here's the evidence of it just blows my mind what they can do. So this is they call it evidence for sea level fingerprints. So signs of excuse me, of sea level rising. And what you see is the trend in the change in time of the sea level between, you can see the date here, it goes I think to 2014. They're going to tell me the start date, 2002 to 2014. So that's the period of a satellite called the Grace satellite, which measured the mass field of the Earth. So they so when it's red, it's positive in units of millimeters, so up to 50 millimeters, so 5 centimeters, down to -5 centimeters in deep blue. And I guess the point is, as the time mounts, and as you approach to 2014, you see a really strong signal. It's not a linear constant trend. It's like it's accelerating at the end, which is frightening. But here we're 2009, 10, 11, 12. You see it's getting deeper and deeper blue here. And when it changes back to red, that's because we go back to 2002. But it's becoming, as time progresses, it becomes more and more blue here around Greenland. That's because of the loss of the ice around on the Greenland. Sorry, I should have started by the fact that on top of Greenland is an ice sheet. Ice sheet is just a huge glacier, and that covers the entire continent of or entire island of Greenland. And I've forgotten the thickness of this thing. It's at least 1 kilometer. It's something I should know. It's I want to say 2 kilometers, but I can't remember exactly. But it's at least 1 kilometer thick, right? It's this huge ice sheet. It's several kilometers thick in Antarctica. There's another ice sheet in Antarctica and one in Greenland. And so it's just amazing, right? You can see the loss of this ice sheet and the gravitational pull, but the sort of the lowering sea level is the blue. It's only near Greenland, and Iceland happens to be close enough to Greenland that I wish I could pause it and then you could just see there, like there it's getting blue, but then actually if we go down here, you get the signal averaged over that 12-year period, or integrated over that 12-year period. Or no, I guess it's expressed as millimeters per year. So it's averaged, the average rate of change. And it's deep blue around Greenland. That's the melting of that ice, which leads to fresh water being distributed all over the world. So most of the world sees a sea level rise. Unfortunately for the people that live, in a lot of these poorer areas, that's where the sea level rise is the biggest. So it's largest in the tropics. Yeah, so this is from, as I say, measurements from from this GRACE satellite mission. So these are measurements, and but the interesting thing is that the geophysicists they anticipated this happening, right? They did the calculations and figured out that it's not just a uniform sea level rise. There's this gravitational attraction is significant, or is very important. Yeah. So
thank you, sir, for these clarifications.
Yeah.
I really appreciate it. Sorry if it sounds like because you didn't see my facial expression, so I mean it in a sarcastic way. So because the purpose of our master is how to take advantage from the marine renewable energy. So if there is a way, yes, one of the purposes is to stop melting these ice. So if there is no way, if it will not be like this in a local area, we will not have this. So which is the purpose from letting ice melt. So thank you for this clarification. It's really now with the visualization, it's all clear.
Yeah, good. Thanks. Yeah, and that's why it's important to ask questions, right? So don't hesitate to
Please share the link of the website.
Yeah, okay. Yeah, how about I do that right after the class, and if I forget, don't forget to, or don't hesitate to remind me. Okay, so we were talking about I was introducing the notion of tensors. I'm not sure the other professors are going to talk about tensors, but I'm sure they're going to use them even if they don't give them their mathematical name tensor. They're going to start using matrices and which represent tensors. So my philosophy is it's good to just tell you what these things are, and the nice thing for you is these are already familiar concepts. The scalar is a tensor of rank 0. It sounds like a trivial example, but it's nice just to bear in mind. If you want to represent, for instance, the temperature in this room, or the mean temperature or the temperature at a point, it's a number, right? It's not a vector with direction or something. It's just a number, a real number. So we say that's a scalar. So you could say it's a tensor of rank 0 because you didn't need any indices to tell you which component it was. And it's the just to drive home the conceptual point, you could change your coordinate system and it wouldn't change the temperature, obviously. So that's a tensor of rank 0 would be temperature. Pressure at a point is another tensor of rank 0, just a scalar. A vector, so a vector has both magnitude and direction. Forces are vectors because you have a magnitude of the force, but also a direction, velocity, displacement. These are vectors, and you need one index to give the 3 components in a 3-dimensional space. So that becomes a tensor of rank 1. Here's one I wanted to spend a little bit of time on. It's another vector, but it's a surface element. So we don't normally think of a surface or an element of a surface as being a vector, but we're going to represent it as a vector. So the obvious question is what's the direction associated with the surface? Well, surface does have a direction, right? And so we could. I apologize for the people at home, but I have a picture on the next slide. Actually, why don't I just go there? Yeah. So here's my here's a vector. Or it's a little area, little element of area, because for us, we're always going to be dealing with little, delta A is a little area of the magnitude of this area is just the length in the x1 direction, delta x1, times the length in the x2 direction. I'm not so gifted at these perspective diagrams here, but this little square, it's supposed to be a square in the x1, y1 plane. So with sides parallel to the x1 and x2 axes. So its length is delta x1 times delta x2. That gives the area, the magnitude of the area. The direction is a unit vector pointing orthogonal to the surface. So there's my little vector pointing parallel to the z or x3 axis. So that's it's the direction of this delta A vector, the area vector, is in this particular case is along the x3 axis. Of course, I chose that just as an example that's a little bit easier to draw. You can imagine a little area pointing in any direction. So that's how areas can be represented as vectors. And it has to be, for it to have a well-defined direction, it has to be a planar surface. And of course, even a curved surface, if you take just a tiny element of it, is to a good approximation, is a little planar surface tangent to that surface. So that's a vector of rank, or that's a vector, a tensor of rank 1, because you have one index for that unit vector pointing in the direction normal to the surface. But now I want to, in fluid mechanics, we're going to make use of tensors of rank 2, mostly for physical quantities. And then we have this third rank tensor that I've already shown you, which is just a useful mathematical device. So this stress tensor, sigma ij, is one of our most important tensors. It's of rank 2 because it has 2 indices. And the first index gives the direction of the force and the, but it's a force per unit area. Which area? Well, the area with unit normal in the j direction. So that's why you need the second index here. The j, it's a force. It gives you a component of force. So you need one index to tell you the direction of the force, but then you need the second index to say acting on which surface. So the j index tells you the direction of the normal of the surface. Okay, we're going to go into much more detail on this stress tensor in a minute, or for the rest of the class actually. And another tensor I've already used is the Kronecker delta. It's a rank 2 tensor, has 2 indices, be represented as the identity matrix. I'm trying to sort of touch base with matrices because I assume those are more familiar to you. Who's dealt with matrices already? Can you raise your hand? So almost all of you, not uniformly all of you. If you haven't dealt with matrices, you should look that up. If you like, I can, yeah, because that falls within linear algebra, which is kind of this basic thing that we usually take as a starting point, basic linear algebra and calculus. So then, but I can, well, actually this Mary Boas book is a really good book for linear algebra. It's good for all kinds of math, more advanced math, but linear algebra as well. Maybe you can send me an email if you want me to give you more background on matrices and algebra, and then I can point you more specifically to the resources that are important. Okay, so I've already given this example, but I'll just do it. Yeah, actually, so I did do it a bit quickly. And so you might have noticed that I said the direction is along the z-axis, but it could have been pointing down too, right? So there's an ambiguity there. But the ambiguity is resolved in a particular application because well, typically the surface encloses a volume, and then we have an inside and an outside, right? So and the convention is often stated the outward facing normal would be the normal that points outward. Of course, it has to be closed in order for there to be an in and an out, but that's usually the case. Okay, I think I'm not going to go into this. I'm not going to give you the solution today, but I will give you the solution on Thursday. But I'd like you to try and work out the 3 components of the cross product of U and V using this rule about the formula I gave you earlier, and the epsilon ijk is +1 when the ijk are an even permutation, and -1 when it's odd permutation, and it equals 0 when any of the 2 indices are equal. So if I equals j, it's 0. If j equals k, it's 0. So try and work that through. Yeah, if it's trivial for you, it should be very quick. If it's takes you a while to think it through, then that's a good thing. You'll be much more comfortable with that alternating tensor after you've worked it through. And don't forget to do the summation over the I and the J, because they're repeated indices. Yeah, so you should have 2 terms. So there should be 1 term minus another term for each component, okay? So here I'll give you the first, well, I think I already gave you the first one. It's W1 will equal U2 times V3 minus U3 times V2. Yeah. Okay, so I've done 2/3 of the work for you, right? You have to find, well, please try and reproduce that on your own and try and get W2 and W3. Those are the three components of that cross product. And we'll, you know, send me an email if you have a question, or we'll do it together on Thursday. For the rest of the class, we have an hour and, or sorry, we have 45 minutes. I'd like to try and explain how we use this stress tensor to represent the surface forces, the internal stresses, which arise from viscous forces, or which are the viscous forces arising from the relative motion of the parts of the fluid. I guess in fluid mechanics, we talk about fluid parcels. If it sounds funny to you in English, it sounds funny to a native speaker too. Parcels are just, I guess the translation in French would be colis, and I think they talk like that. But we just mean little bits of fluid, right? It's just a useful notation to think of. You have one parcel of fluid here and a parcel there, and if they're moving relative to each other, then there can be stresses between them. Of course, they'd have to be close to each other to feel the stress. But part of being a fluid is that if the fluid is stationary, then there are no viscous forces. Okay, so let's consider a planar surface element. So a small bit of surface that's a plane. So it could be tangent to a more complicated surface of area delta A, and I put a subscript J, so it's a vector. So I'm thinking of this as a vector quantity, the vector being pointed in the direction normal to the surface. The normal I've written explicitly here is NJ. So NJ is a vector with unit norm. In other words, it has length 1. Okay, so that's a surface and a tiny planar surface with a given direction, pointing in this direction, NJ. And we want to specify well, you can imagine that there are forces on that surface. So the force itself will be a vector. So it'll have 3 components. So I can speak of the ith component of that force. And the force, where does it come from? Well, we're talking about surface forces. They come from interactions between the short range of interactions between the molecules. So in other words, it's a force I want to describe per unit area. So and you suspect that it'll be, well, it will be proportional to the area. So I can write delta, meaning it's a small force, and I'm putting the subscript I to indicate the ith component of that force. The P here means at a point that I labeled P in the fluid at a time t. So this component of force is a function of the position and the time, and it equals, well, I'm defining here the quantity called the stress tensor. So the stress tensor is sigma ij. It depends on where I am. So it's a function, sigma ij is a function of p and t. It depends time and position. And it has two indices. So as I said, that was our classic example of a rank 2 tensor. It has two indices, and the I, notice the I corresponds to the direction of the force. So the I is giving me the direction of the force on that surface, and the J corresponds to the index of the area element. So you can think of sigma ij as the component of force in the I direction per unit area along a surface with a normal in the j direction. And then if that's a force per unit area, and I multiply it by this vector area, then that gives me the total force on that surface. And this is just a reminder that I and j take the values 1, 2, and 3 because we're in a three-dimensional space. So as I mentioned before, sigma ij is a second rank Cartesian tensor. So there are 3 times 3 equals 9 components in a three-dimensional space. I can write that as a matrix. So here's what I mean by a matrix. It's just a table of values, a bit like an Excel spreadsheet, except it's well, what can I say here? This is a special matrix in that it's square. It's 3. It has, so the rows are horizontal, right? So it has 3 rows, and then it has 3 columns. Yeah, actually, it's the same language as in French. Vertical columns and horizontal rows. And I've decided to label my indices instead of 1, 2, and 3. I used X, Y, and Z. It's arbitrary, right? They're equivalent. It's just that I chose X, Y, and Z just to remind you that the 1 corresponds to the X direction, the 2 corresponds to the Y direction when they're indices. So I actually prefer the X, Y, and Z here, even though it looks a little bit funny when you have the sum, because you don't think of summing over X, Y, and Z. You think of summing over 1, 2, and 3. But once you get used to it, it's actually nicer to use the letters than the numbers for the indices. Now I'm a bit concerned about, oh, no, okay. So equation 10 tells me that that sigma xy is the x component of the force per unit area on a surface with normal in the y direction. I guess I'm just giving a specific example of what I tried to be general about a second ago. So we can distinguish between 2 types of these stress components. Okay, there's the case of a tangential stress. By that I mean that the force is acting along the surface. So this x sigma xy is an example of a tangential stress because the force, it's in the x direction, but the normal to the surface is in the y direction. Well, x is normal to y, so that means that the force is acting along the surface as opposed to normal to it. So it's the forces along the surface. Of course, it didn't have to be x, y to be along that surface. If the surface is in the y direction, yeah, it has the normal in the y direction, the sigma, what else would be tangential to that? Can you give me the other one that's tangential? Sigma zy, yeah, because z is also tangential to the surface. Z is also orthogonal to y. Yeah, very good. So xy is a tangential stress. Where is it here? Here it is. So that's rho x column y, or rho 1 column 2. But here's another one. X, it's oops, that's not the one. What? Yeah, so this is the other one that this gentleman in the back just gave. Sigma zy has the normal in the same direction, but it has the force in the z direction. These are all force per unit area, right? So in fact, this whole column represents the forces on the surface with normal in the y direction. But this one in the middle, sigma yy, is not a tangential stress because the force is in the y direction when the normal is in the y direction. So that's a force into the surface. So if you like, the sigma yy is like a push, or it could be a pull too, right? We'll get to the sign in a second, but the normal force is pushing in the direction along the normal, or pushing or pulling, and so that's when the indices are the same. So we have another one. Can someone else, or we have two other ones. Can someone else give me, or someone else give me another normal stress component? Can you give me a normal stress component, please?
Normal to what direction?
You choose, not the y, because we already did the y.
In x direction. There is a yx and.
But that's tangential. Yeah, so I'm looking for a normal. So these stresses classify into tangential stresses where the force is along the surface, or so they're that, or they're normal. They're normal stresses. So when they're normal stresses, the force is in the direction of the normal. Can someone give me an example of a normal stress term? XX, sigma XX, the force is in the X direction and it's on the surface with the normal in the X direction. Sigma ZZ is the third one. So in other words, the normal stresses are on the diagonal, what we call the diagonal of this matrix. Now there's a convention in matrix lingo, matrix language, that this is the diagonal, what I'm tracing there, but this is not the diagonal, even though it is, in general terms, that is diagonal. It's not the diagonal of the matrix. The diagonal of the matrix is when the row index equals the column index. So this is 1, 1, or XX, and this is YY. And this is ZZ. So it's row 3, column 3. So the diagonal elements have the indices equal, and those are the normal stress components. So it's a bit complicated, right? We just wanted to talk about forces inside this fluid, and then we realized, well, we had the body forces, which were fairly straightforward, but then we have these surface forces, which, it takes this animal of 9 components to describe it, because we have 3 directions of the force to keep track of, and then 3 directions of the surface to keep track of. But we can classify them in terms of tangential stresses, which are off the diagonal. So we've got 3 up here, the X, Y, and the XZ and the YZ. And then we've got the 3 down here, the YX, etc. Okay, so I can refer succinctly to the diagonal components of the stress by sigma II. So I guess I have a repeated index there, but I don't mean that you do a sum. I just mean when the row index equals the column index, then we're talking about a normal stress. And then these off diagonal components are when I is not equal to J. Those are the tangential stresses. And then normally I would show you this figure from Batchelor's book. But I decided to draw it out for you yesterday so that I could show it to the people at home. Actually, I should be careful that that they're not posing questions in the chat. Okay. Yeah, so even at home, don't hesitate to interrupt me or you can discreetly type something in the chat, but if I don't see it, you might have to speak up. And
okay.
Okay, thanks. So here, I've just taken this from figure chapter 1 of Batchelor's book. And I want to look at a little cube. And well, I don't want to commit myself to, it's a little box, a little 3-dimensional, I guess a right parallel pipette, but a little box with flat edges. And I've drawn it in the X1, X2, or the XY plane, but it has a depth in the 3rd direction, which is delta X3 that we can't see because we're just drawing in 2 dimensions, and it's much clearer actually to draw in 2 dimensions than try to make some perspective thing, which then becomes ambiguous. So it's just, except that it has a thickness X3 and it has a width at delta X1 and a height delta X2. And we want to talk about the forces on the 4 surfaces. We won't talk about the other 2 surfaces because they exist, but if we understand these, then we've essentially understood the whole story. Or it's an easy generalization, even if it's hard to draw, to understand the others. So let's start with this surface here. I've drawn its normal there, right? In the X2 direction. And I want to talk about the force in that direction. So that's a normal stress. So I take the sigma 2, that's the force component in the X2 direction because of the first 2, per unit area with normal in the X2 direction because of the second 2. So that's sigma 2 times, now I have to get the force, I have to multiply by the area. So the area, well, it has a length delta x1 here. And then in the direction we can't see, it has a thickness delta x3. So that's the force in that direction, which I've represented as a little arrow. Okay, hopefully that's clear. And now I can talk about another force. I can talk about I could talk about two other forces, but one will be in the z direction. So let's not deal with that one. The other one will be in the x1 direction, right? We've dealt with the force in the x2 direction. There it is. But there's a force on this surface in the x2 direction. So that's sigma 1, first index to indicate the forces in the one direction, times, or second index 2, because it's this surface with normal in the x2 direction. Now we have to multiply that by the area, right, to get the total force. But it's the same surface as we just dealt with. So it's this surface here. It's delta x1 times delta x3, delta x1 times delta x3. So that's that little force there. Okay. Let's see. I can let's jump. Actually, let's go down here and talk about this surface here. Actually, but before I do that, I just want to talk about Newton's third law and say that, and also I have to talk about the fact that about conventions here. So the normal is pointing upwards here. And so so I have a little box of, or a parcel of fluid that's in the shape of a box. And so I've drawn all my normals in the outward direction. That's a typical convention. You could say at the start, I'm going to consider the inward facing normals, but the standard is to choose the outward facing normals. So so that's why these normals are all pointing outwards. And then there's another convention that we have to decide upon, which is we're talking about the forces of acting on the surface. And the convention is that we're talking about the force that's represented here is the force exerted by the exterior fluid on the interior fluid. Okay, so when I say the force is this, it's sigma 2 times this area here pointing in that direction. Which force is that? It's the force of the fluid out here acting on the fluid in there. So it's kind of like, you can imagine why that's the convention. It's like, well, we want to know what's happening to that fluid parcel, right? So we want to find all the forces acting on that fluid parcel, and then we're going to talk about how it's accelerating eventually using Newton's second law. It has a certain mass. It has a the total force divided by the mass is going to give the acceleration of this fluid parcel. So, so I want to talk. So the convention was that the fluid exterior is acting on the fluid interior, and that gave this force. that I've drawn here, and we expressed it with the stress tensor. So the convention implies the meaning of the stress tensor. But if that exterior fluid is causing this force on the interior fluid, then by Newton's third law, this fluid inside, below the line, is exerting a force of the same magnitude but the opposite sign on this fluid above the line here. Okay, so that's going to be useful now if I go down here, because now I want to talk about the fluid, well, this force on this surface. But see, I have this funny thing where the normal is pointing in the minus x2 direction. Well, what I could do is, well, I just want to, what I want to say is, well, that's just -1 times the force when the normal is in the y2 direction. So I can just because my normal is in the -y2 direction, my force will be in the per unit area will be in the minus x2 direction. Did I say y2 direction? Yeah, I meant x2 direction, which is the y direction if you're using xy. Yeah, so let me, so that was my justification for the force being in the minus x2 direction when the normal is in that minus x2 direction. And how that works out is that this force is has the same form as the expression up there. So it's sigma 2 for a force in the x2 direction, but it'll be minus that times the area in the with normal in the positive x2 direction, but we have the minus x2 direction, so those two minuses cancel and give us sigma, just plus sigma 2 times the area, which is just the length here, delta x1 times the thickness delta x3. So it's the same area here as here, but the force is now point in the opposite direction. This force is not necessarily equal and opposite to that one because this stress tensor, remember, is a function of position in the fluid, right? So I'm at a higher position here than there. So in other words, the gradient of the stress tensor is going to be crucial in determining the forces that make this fluid parcel move. Yeah, so on this surface here, this is a tricky, yeah, this surface is tricky in two ways. We have that force to work out. There's one more force acting on this. Well, there are two other forces. One again is in the z direction, but the other one is in the x direction, x1 direction. But I didn't have the arrow pointing this way. I put the arrow over there for the same reason, is because the normal is pointing in the minus y, or the minus y direction, or the minus x2 direction. So when you take sigma 1, 2, it's giving you the force in the minus x1 direction, because the normal is in the minus y2 direction, or minus x2 direction. And so that the magnitude of that force is sigma 1, 2 times this area, force per unit area, times this area, and the area, we've already worked that out. It's this length times that thickness. Okay, so there's the two forces in the plane acting on this surface. We've done that surface, that surface. We could do this surface and this surface. Maybe I'll do one more. Let's do this surface, because this one's a little bit easier, right? Because the normal is in the x1, the positive x1 direction. So the force in the x1 direction is the normal force. So it's sigma 1, 1 times the area here, which is the length times the thickness. So the length is delta x2 times the thickness that we can't see, delta x3. So that's that force. But then there's the tangential, well, there are the two tangential forces, one in the z direction that we'll ignore. And then there's the tangential force on this surface, which is in the y direction, or the x2 direction. So that's sigma 2 normal in the x1 direction. So sigma 2, 1 times this area. Well, it's the same as this area. And then we've got the corresponding term on this side. And then I deliberately left out one force here, just to get you to think about it. Can anyone see which force I left out? It's a little arrow that should have been drawn somewhere. It's an arrow pointing down, that's right, yeah. Does anyone see it? So, sorry? Pardon me? It's, well, let's look at the normal. There are four normal forces, this one, that one, and that one, right? So I got my four normal forces. I mean, there's six, but there's, the other two are out of the plane. Now, so for each surface, I should also have two tangential forces, only one of which I'm going to draw. So for this surface, there's the tangential force. For this surface, there's the tangential force. For this surface, I've got a tangential force going in the negative direction because the normal is pointed in the negative direction. Do you see it now? Yeah. So for this surface, I have a tangential force, or I have the normal force, but I need a tangential force. Should it go up here? No, it should go down because its normal is in the minus x1 direction. So it should point down here. So that's the arrow I missed. But now I've left out the label for you. Can someone tell me the symbols? What stress tensor component do I need? Guess you could figure it out by process of elimination, right? Sigma 2, 1. It's actually the same as this one here. It's a force in the x2 direction, actually minus x2 direction, but its normal is in the x1 direction, or actually the -1 direction. Yeah, so it's sigma 2, 1, just like that, times, sorry? It should be the same as this, right? Because it's this area here, delta x2, delta x3. So that's what I wrote. Just if you're reading this at home, I wanted to give you the answer so that you're not frustrated. So I just repeated that figure 3 times, progressively giving you the information. So there it is with the arrow and the numbers. Okay, we're rapidly running out of time here, but I might not finish everything, but we'll see how far we can get. So the now, so I said to represent these stresses, it looked complicated, right? We had the 3 diagonal terms, and then we had 6 off diagonal terms to represent the stress, the tangential stresses. But it turns out it's fortunately things are not quite so complicated, because this stress tensor has some symmetry. In fact, it has to be symmetric. You can write that mathematically by saying, or conveniently in this tensor notation by saying sigma ij has to equal sigma ji. It's not immediately obvious, but actually, if you think of this fluid parcel, I think you can work out that there would be a torque on this fluid parcel. Now, remember I said sigma here can be different than sigma there, but if you take the limit that this cube goes to 0 volume, that's what we mean by a fluid parcel, by the way. It's just a little cube like this. It doesn't have to be a cube, but it's convenient that it's a cube or a box. But it's any size you like. So you can imagine you're allowed to take the limit where the volume goes to 0, or all 3 lengths go to 0 at the same rate. And so this thing could shrink. And I think you can, I don't think I've actually done this before, but I think you can convince yourself that there would be an infinite torque. Actually, what would go to infinity would be the torque divided by the moment of inertia. Yeah, so maybe it's a bit complicated, but you would, actually, I'll think about that some more for Thursday, but I think the net result would be if this thing weren't symmetric, so if this sigma 1, 2 was not equal to sigma 2, 1, then this fluid parcel would accelerate in a rotation. It would rotate infinitely quickly. So that's that doesn't happen, and the reason it doesn't happen is that sigma ij must be equal to sigma ji. In terms of matrices, what that means is that the component here, sigma xz, has to equal sigma z. Sigma xz has to equal sigma zx, and this sigma yx has to equal sigma xy. So in other words, remember this was the diagonal. So components opposite each other across the diagonal have to equal. So once you know these 3 components, you know these 3 components down there. So there are only 3 plus 3 independent components of the stress tensor. There are only 6 degrees of freedom here. So the nice thing is it's simplifying a little bit. only 6 independent components of this matrix. And then there's this is not so useful in practice, but conceptually it's useful to know that when, if you remember from your linear algebra, which you studied a long time ago, whenever you have a symmetric matrix, you have the possibility of choosing a reference frame such that the matrix has a diagonal representation. So that's what's called a similarity transformation. And I guess you guys studied engineering, so I'm not sure when you studied this, but the students at the university here, we study that in second year. We diagonalize matrices. So does this sound familiar to you? Yeah. Okay. At least for some of you, you've diagonalized matrices. But just maybe for those who haven't heard this before, just trust me, whenever you have a diagonal or a symmetric matrix, you have the possibility of choosing a different coordinate system. It's still a rectangular Cartesian coordinate system. You've just changed the orientation of the axes via rotation, right? You didn't sort of move the center, you just rotated the axes. Sorry, I guess that's hard for people at home to see, but you're keeping the origin the same, you're just rotating the axes. That changes the components of this matrix, right? Because it's a tensor, and you can choose. You don't have to necessarily go through all the calculations. You can just know that because it's symmetric, we know it exists a coordinate system such that the components become 0 if they're off the diagonal, and not necessarily 0 when they're on the diagonal. So all that amounts to the following. I can choose a reference frame. I'm going to call it sigma prime now, just to indicate that it's a special. I chose my reference frame such that this was true. The diagonal components are 0. So that's kind of interesting. So you might say, well, why did we have to worry about all those tangential stresses if we can always show that they're 0? The thing is, remember, this stress tensor varies throughout the fluid, right? So you want to just, for convenience, you want to choose one coordinate system. And then if you choose your one coordinate system, okay, it's diagonal here for this instant in time. There'll be off diagonal terms in general elsewhere, or at the same place, but later in time. So, so this isn't of great, as I said at the start, it's not of great practical use, but conceptually it's interesting to know that what are these internal, these complicated internal stresses. Well, there's always a reference frame in which they have a simple interpretation. They all collapse onto these normal. If we chose our coordinate system correctly, they'd be normal stresses. So they would be compressing or pulling apart a little cube oriented the correct way, right? A way we're not free to choose. We have to choose it so that the stress tensor becomes diagonal. Just for I guess if as a reminder for those who have studied this, the way you change your matrix is when you change your orientation, your coordinate system. It's called a similarity transformation, and you need to change the matrix with another matrix, and that matrix is called the basis transformation matrix. It just represents the fact that you've changed the orientation of your axes, and you have to apply it twice. You have to find its inverse, and you have to multiply it by the stress tensor twice, and that gives you the components of the stress tensor in the in this new coordinate system. Maybe I just have time to tell you that how do we define pressure in a fluid? Well, pressure is related to those normal stresses, right? Because pressure is trying to squeeze the fluid parcels. So it's a normal force and normal stress. And we can define the static fluid as being the what's called the trace of the matrix, or the sum of these diagonal components, the sum of the normal components. That's called the trace. And then if you take the trace of the matrix and divide it by 3 and put a minus sign in front, that becomes the pressure. So the pressure is like minus the average of the normal stress. That's a static fluid pressure or thermodynamic pressure. Why is it minus? Well, if we go back to that diagram, we notice that just by convention, our normal stresses, if these sigmas were positive, sigma or the diagonal sigmas, sigma 2, 2, sigma 1, 1, if these were positive, then there would be forces pulling this cube apart. But pressure is doing the opposite, right? It's squishing the cube together and trying to make it smaller. So the pressure is minus the average of these normal stresses. And in particular, that's the thermodynamic or static fluid pressure. So pressure is a normal stress. And I'll leave you with an exercise here. I wrote it, this morning I decided to write it differently than in the notes that I sent to you. So I think when I go home, I'm going to email you the link to that thing about the Greenland ice sheet, and which is just of general interest. But I'll give you the new notes of this exercise, in which I try and give you some more background information and then give you a hint to help you figure out how to write the stress tensor for a static fluid. Yeah, and then on Thursday, I guess we'll have to start here on viscous forces. But we've made it through the tough part of the class, so hopefully it'll be sort of smoother sailing from here. Yeah. So let's stop there, and don't hesitate to ask me any questions by email. Yeah, try and work out those exercises. I'll try and figure out how I can make this recording of the lecture available to you. I don't know if that's useful or totally necessary, but maybe for the people at home who missed the first part of it, you can see it or see it and listen to it.